Using the miracle of modern mathematics, you can rewrite that equation. And now this is a small step for a mathematician, but a giant leap for a physicist. Not because it's that hard to put this term over there, most of us could do that, but because it now represents something very different when it's on this side of the equations. Here it was somehow a geometric quantity. When it's here, it looks like a new contribution of the energy and momentum of the universe. What could contribute a term like this? And we know the answer. Nothing. By nothing, I don't mean nothing, I mean nothing. If you take empty space, and that means get rid of all the particles, all the radiation, absolutely everything, so there's nothing there. If that nothing weighs something, then it contributes a term like this. Now, that sounds ridiculous. Why should nothing weigh something? Nothing is nothing. And the answer is nothing isn't nothing anymore in physics. Because of the laws of quantum mechanics and special relativity, on extremely small scales, nothing is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Now again, that sounds like philosophy, like counting the number of angels on the head of a pin, or religion, or something useless. I shouldn't say, Dan Dennett is here, I shouldn't say philosophy is useless, but anyway, he's also a friend. But the point is, we can't measure virtual particles directly, but we can measure their effects indirectly. And in fact, they're responsible for the best predictions in physics. Here, by the way, is actually an animation that was shown at the Nobel Prize ceremonies about 5 years ago by a friend of mine who happened to win the Nobel Prize for developing the theory that produced this. This is the space inside of a proton, the empty space inside of a proton. Not where the quarks are, but the empty space between the quarks. And this is an animation, but it's an exact animation coming from physical calculations. This is what the space looks like. Now, how do we know that? Well, there are a lot of reasons, but one of the things are, it turns out most of the mass of the proton comes not from the quarks within a proton, but from the empty space between the quarks. These fields popping in and out of existence produce about 90% of the mass of a proton. And since protons and neutrons are the dominant stuff in your body, the empty space is responsible for 90% of your mass. So these empty space is vital to science, and these calculations are vital to understanding not just protons, but electrons and atoms, and produce the best comparisons, and I will repeat this, the best comparisons between theory and experiment in all of science. To 10 decimal places in quantum electrodynamics, using these calculations, we can get the right answer. It's amazing. So, if that's the case, let's calculate the energy of nothing where there's nothing else. And when we do that, we come up with a calculation which is pretty bad. It's the worst prediction in all of physics. We calculate, you can't even see it, I think, there's a 1 at the end of that. We calculate that the energy of empty space is a gazillion times the energy of everything we see. That, as I say, is the worst prediction in all of physics, which is why we didn't talk about it for a long time. We calculate that empty space should have an energy of 120 orders of magnitude more than galaxies and stars and people and aliens and all the rest. And if that were the case, we just wouldn't be here. So we knew something was wrong with this calculation. It's been around since I was a graduate student. And we knew what the answer was. Theorists always know the answer. They're just sometimes right. We knew the answer was 0, because it's the only sensible answer. Because, you know, you can't cancel a big number like this. Let's say the energy of empty space was comparable to the energy of everything we see. Well, we'd have to cancel this big number to 120 decimal places and leave a finite answer in the 121st decimal place. No one knows how to do that in science. But 0 is a number we can get beautifully in science. We use mathematical symmetries. Things cancel, equal and opposite things cancel all the time in science because of symmetries of nature. So we knew the answer. We didn't know what the symmetry was, but we knew the answer was 0. And we could go to bed at night and that was fine. But you know, the neat thing about cosmology is it's really a science. And science is empirical. Knowing the answer means nothing. Testing your knowledge means everything. And so the question is, we should test what the energy of empty space is. And how can we do that? Well, we weigh the universe. How do we do that? We stand on the shoulders of giants. This is a picture I took in an island off Sweden, which used to be an island off Denmark now, which used to be an island off Sweden. It's the island of Ven. I think I said that right. And this guy, if you look carefully, he doesn't have the end of his nose. His name is Tycho Brahe. And he, as many of you know, laid the basis for Newton's law of gravity by doing nothing other than spending 20 years on his back, a noble tradition, in this case, looking up at the sky without a telescope, measuring the positions of the planets around the sun. And then he was a crummy feudal lord. He got kicked off that island. He gave the data, went to Prague, gave the data to a hapless assistant named Johannes Kepler, who again spent 20 years without a Macintosh trying to interpret the data, and fudged it, we now know, and came up with, of course, Kepler's laws, which led to Newtonian gravity. And the point is, we can use gravity to weigh the universe, including the weight of empty space. Now, why do we care? The reason I got into cosmology. General relativity tells us that space is curved, and therefore the universe can be a one of three different geometries: open, closed, or flat. Now, I can't draw pictures of three-dimensional curved universes very well, so here are pictures of two-dimensional curved universes. This is a closed universe, a sphere, a surface of a sphere in 2 dimensions. But if we had a closed three-dimensional universe, it's very simple. It'd be very similar. If our universe was closed, if we looked far enough in that direction, we would see the back of our heads. Light would go around the universe. And an open universe would be infinite in spatial extent, as would a flat universe. And that sounds really nice, but it's irrelevant. The really important thing is, in a universe full of matter, a closed universe will expand and stop and then recollapse in a big bang, in a big crunch, the reverse of the Big Bang. An open universe will expand forever, and a flat universe will expand and slow down but never quite stop. And that's why we wanted to know which universe we live in. And as I say, that's why I wanted to learn about it, because once I knew which universe we lived in, I would know how the universe ended. Okay? And so, weighing the universe tells us what the curvature of the universe is, and that's why we want to weigh it. So here I want to just show you in the next few minutes how, in fact, some of the most remarkable developments in cosmology, and then tell you how they completely changed our picture of the universe so that we understand that the universe we live in is the worst of all possible universes to live in. Okay, just so you know where we're heading. This is a cluster of galaxies. Each dot in this picture is a galaxy. Again, amazing to think about. Remarkable. Every one of these galaxies contains hundreds of billions of stars, and perhaps civilizations, some civilizations that are mired in religious gunk, other civilizations that have moved beyond, and other civilizations that are long dead, because this is about 3 billion light years away. 3 billion years ago is when that picture was taken, basically. Now, clusters of galaxies are the biggest bound objects in the universe, so if we could weigh them, we can weigh all the mass in the universe, and we can weigh them now. We can weigh them by using general relativity. Because in this picture is a remarkable phenomena that Einstein first predicted in 1937, though he said it would never be observed. He underestimated observers. If you look at this picture, you'll see these blue things, these weird blue things. That is a phenomenon that we now understand as gravitational lensing. Einstein told us that a mass will curve space around it. And he realized, therefore, if you had a big enough mass and you have a source of light behind that mass, the light can bend around that object and come back and be magnified, just like my glasses magnify things. Or, like a cut glass goblet, if you look through it, I'd see many images of this room. Mass can act like a lens and magnify things and split images, and that's precisely what we're seeing. All of these blue things are different images of a single galaxy located about 3 billion light years behind this cluster. Gravity is magnifying the image, distorting it, and bending it. Remarkable. Truly remarkable. But because we understand general relativity, we can work backwards and figure out how much mass must be in that system and where it is in order to produce that image. We can weigh the system using general relativity. And when we do that, here's an inversion by Tony Tyson, who's now up in Davis. This is the system, and the spikes are where this is where the mass is in this system. The spikes are where the galaxies are. But you notice most of the mass in this whole system of clusters of galaxies is not where the galaxies are. It's between the galaxies. It's where nothing is shining. About 50 times as much mass in this system, and in all systems we can measure, comes from stuff that doesn't shine. And physicists, with their linguistic perspicacity, have called it dark matter. And we now understand that 90% of the mass of galaxies and clusters, including our own Milky Way galaxy, is made of stuff that doesn't shine. And that isn't maybe that exciting because there's lots of things that don't shine. You don't shine if I turn the lights out. Well, those of you from Los Alamos might, but the rest of you don't. But so it could be snowballs or planets or boring stuff, but it can't be. Because for reasons I don't have time to explain, we know how many protons and neutrons there are in the universe. We can actually measure that. And there aren't enough to make up all this dark matter. So we are pretty convinced that that dark matter is a new type of elementary particle. Something that doesn't normally exist on Earth. And the great thing about that is that means the dark matter isn't just out there, it's in this room. As you doze off, it's early in the morning during this lecture. It's going right through your body. And that means we can do experiments here on Earth to look for it, which is remarkable. And in fact, I think well, I'll show you an experiment in a second. But by measuring the mass of these systems and this dark matter, taking normal matter plus dark matter and weighing it, we now have determined how much stuff there is in the universe. When physicists have an important number, they give it a Greek letter all the time. So we call it omega. Omega is the ratio of the total amount of stuff we know is in the universe divided by the amount of stuff you need to make a flat universe, the boundary between an open and closed universe. If it's less than 1, the universe is open. If it's greater than 1, the universe is closed. And we have now measured unambiguously that there's only 30% of the amount of material in the universe, including dark matter, to make the universe flat. Okay, we'll come back to that in a second, but I just want to show you that we actually do things in physics. This is an experiment to look for dark matter. It's a boule of germanium. And there are experiments like this all around the world, in mines, deep underground, because you want to shield out cosmic rays, because there are lots of them going through your body right now. You want to only see the dark matter, and the dark matter particles on average will go right through the Earth, we think, because they don't interact strongly. And most of the time right through this detector, but every now and then one of them will bounce off an atom, the nucleus of an atom of germanium. Heating, and the first thing we do is we cool this thing down to 1/1000th of a degree above absolute zero, which can easily be done nowadays. And if one of these dark matter particles bounces off a nucleus of an atom, it'll heat the whole thing up by 1/1000th of a degree. And we can measure that. And there are experiments here in South Dakota and in Europe, all over the world, looking for dark matter. We haven't found it yet. The other exciting possibility, which I should really indicate, which is one of the reasons people are very excited this year, is we may not have to wait for the universe to give us dark matter. The Large Hadron Collider, which is turning on this next month in Geneva, before it creates a black hole that will kill us all, we think actually might, by recreating the early conditions of the early universe, create the very particles which were last created at the beginning of time. So we may first see the dark matter by creating it in Geneva. It's a race. Okay, but to go back to this number here, this is a real problematic number. We now know the universe has only 1/3 the amount of matter to make it flat. The problem is that theorists like me knew the answer. The universe must be flat. Why? Well, there are two reasons. There's the one I normally say, which is it's the only mathematically beautiful universe, which is true. But there's another reason I don't usually talk about, but I'll talk about here. It turns out that in a flat universe, the total energy of the universe is precisely zero. Because gravity can have negative energy. So the negative energy of gravity balances out the positive energy of matter. What's so beautiful about a universe with total energy zero? Well, only such a universe can begin from nothing. And that is remarkable. Because the laws of physics allow a universe to begin from nothing. You don't need a deity. You have nothing, zero total energy, and quantum fluctuations can produce a universe.